Sowers. I'd like to thank all the witnesses for your testimony. The chair recognizes himself for 5 minutes for questions. Mr. Crusan, how could NASA leverage private sector technologies, products, and services on future exploration concepts, such as the potential deep space gateway or the hypothetical deep space transport? What elements are better suited to partnerships, and what aspects are more appropriate for a government-owned and operated effort?
So, Mr. Chairman, yeah, we've been analyzing those exact cases that you've been asking about. We have our Next Step initiative related to the gateway activities and how we construct and actually build that critical infrastructure. And we're trying to find that proper balance between government objectives and commercial objectives, both in the creation of that fundamental infrastructure, but also then in the utilization of that infrastructure as well. Lunar Catalyst, and now with the potential to buy Lunar Landed Services, are another extension of that. Instead of building technologies that are only for our own use here at NASA, but building technologies that are fundamental to the industry demand that they need as well. So through Catalyst, we've been sharing the vast wealth of knowledge that we have at NASA, sharing it with the U.S. industry openly to allow them to make the maximum best use of that. In every one of these endeavors, we have to tread carefully, though, to find that proper balance, and that's why we've been so deliberate about what we've been doing.
Well, then that'll lead into the next thing I'd like to ask you about, the potential pitfalls of leveraging private sector investments in space. Are there any areas about which we should be cautious when it comes to partnerships for lunar exploration?
Yeah, so in a couple areas of alignment of incentives. So expanding the marketplace as a function of commercial demand and government use as well. So trying to get a proper balance and making sure that the government isn't expecting a higher level of performance that isn't commercially sustainable in the marketplace, and getting that balance correct. So buying services at a rate which the industry is going to utilize for non-NASA use as well is one of the strong pitfalls that I would advise.
Okay. And then to Mr. Richards and Thornton and Alexander, I'm pleased to see such a diversity of lunar landing capabilities being developed by your three companies. And it shows how the United States continues to lead the world in developing innovative and affordable solutions. Can each of our industry witnesses briefly explain what makes their lander unique and different from the others? And so the committee can better understand the differences in the capabilities between your services. We'll go with you, Mr. Richards, first.
Thank you, Mr. Chairman. So Moon Express's approach has been to establish a family of vehicles that begins small and can grow. With a partnership with NASA, not presuming a dependency, but looking at the long tail of the market where we can do for lunar access what CubeSats did for access to low Earth orbit. We believe there's a big market here. So we're starting with a microlander that can go in a very low-cost launch vehicle. When we started Moon Express, we were looking at missions that might cost $100 million or more to get to the moon. With the combination of the current technology and the low-cost vehicles that are coming on the market, we can do initial precursor missions for under $10 million of our cost. But those can scale up, and our modularity is key. So like rockets, and especially being manufactured, take advantage of modular systems, and the stages don't get changed over time. Our basic propulsion module scales up into larger and larger lander systems that can reach the moon and deliver materials back.
Thank you. Mr. Thornton.
Thank you. So we are developing the Peregrine Lunar Lander. From the get-go, we are market-focused. So we say, okay, what's the market out there for payloads? What size is necessary? And then we design a lander and the scale that's appropriate for that. So what we have determined is 265 kilograms of capacity serves the majority of the existing market for payload delivery. Our first mission to the moon flies that commercially viable craft right from the get-go. It's a single-stage secondary vehicle that flies on a United Launch Alliance launch vehicle to low Earth orbit, and then we fly the rest of the way to the moon. Once on the surface of the moon, we become the local utility. So we provide power, we provide communications for payloads that come with us. Some payloads can stay attached to the lander. Some payloads can deploy and drive across the surface and use our Wi-Fi on the surface to talk back to Earth. So the lander itself is designed to be a simple, robust system. It's single stage, there's no separations, very few mechanisms to actually move on the spacecraft, so we're all about simple reliability for robust delivery. And what we have found from our customers is that customers are very sensitive to any changes, substantial changes in spacecraft. Customers around the world tell us that if you change your spacecraft configuration, mission to mission, that they're going to think of that next launch as a demonstration launch, and they want to make sure that it's a proven capability. So that's why we have a single spacecraft designed from the get-go to address the commercial market. And we believe that it's affordable enough to get that first flight demonstrated and to capture a large portion of the international market.
Thank you. Now we'll go to Mr. Alexander.
Thank you, Mr. Chairman. Blue Moon is designed as a large lander, so it is designed to take more than 10,000 pounds to the lunar surface when launched on an SLS, a NASA SLS rocket. So that vehicle, that same spacecraft, lunar lander, can be flown on a variety of different launch vehicles, ranging from 1,000 pounds of payload delivered to the surface all the way up to more than 10,000 pounds. So it's a single design, does the in-space transfer as well as the landing down to the surface, and carries with it that large payload capability. So it is designed to enable other missions. It's designed to enable NASA to pre-position logistics for future human missions, to provide resource utilization missions, delivery and access to the surface, or to provide landers like Resource Prospect a way of actually getting to the surface. It's repeatable, scalable, and based on proven technologies.
Okay, thank you very much. We appreciate the witnesses. Now I'd like to